Hello everyone, my name is Yunfei, and today I want to talk about failure. Specifically, why classical computer vision fails, not because the algorithms are poorly designed, but because the scene itself makes recovery structurally impossible. The title of this survey is From Occlusion, Specularity, and Repeated Texture to Identifiability Failure in Classical Vision. And over the next 25 minutes, I want to walk you through what that means and why I think it matters. Let me start with motivation. When we think about why vision systems fail, we tend to blame the algorithm. The matcher was not robust enough, the network was not trained on enough data, the model was too simple. But I want to argue for a different framing. The difficulty is often informational, not algorithmic. It lies in the mapping from the three-dimensional world to the two-dimensional image. The mapping is many to one, it collapses depth, it hides surfaces behind one another, and it entangles material appearance with illumination. The result is that certain scene configurations make recovery fail structurally, regardless of how clever the algorithm is. And critically, these configurations are not rare or exotic. Walls occlude furniture every day. Glass reflects its surrounding in every office. Tiled floors repeat the same pattern across every kitchen. These are the expected conditions of natural environments, not edge cases to be filtered out. So, what are these configurations exactly? This survey focuses on three. The first one is occlusion. When one surface hides another, the hidden surface produces no measurement in the occluded view, no pixel intensity, no gradient, no value correspondence. The data is simply absent. The second is specularity. When a surface reflects light in a view-dependent way, its appearance changes as the camera moves. This violates the photometric assumptions that underlie most classical vision algorithms, creating misleading signals about geometry. And the third one is repeated texture. When a surface has a periodic pattern, like a brick wall or a tiled floor, multiple scene points produce nearly identical local appearances. And when a surface has no texture at all, it produces no distinctive appearance at all. In both cases, correspondence is defeated. Now, each of these is interesting on its own. But what I want to argue is that they all point to the same conclusion, which is identifiability failure. That is the solution situation where the image data simply cannot determine the answer, no matter what algorithm you apply. And that reframing from why does the algorithm fail to why is the scene non-identifiable is the core contribution of my survey. Before we go into the innovative failure modes, let me set up a compact theoretical toolkit. The foundational observation is that most early vision problems violate Helmholtz conditions for well-posedness. Solutions may not be unique or may not depend continuously on the data. The classical response is regularization. Impose a smoothness prior to select from all solutions consistent with the data, the one that varies least. This worked in many cases, but Terzopoulos showed that smoothness regularization fails precisely where it is most needed, which is discontinuities at depth boundaries, at motion boundaries, at reflectance edges. So regularization both helps and has a structural failure mode of its own. The key diagnostic tool we use is the Fisher Information Matrix. Kanatani showed that when this matrix is singular, Certain parameters are mathematically non-recoverable from the data. No estimator of any form can determine them. This is what I mean by identifiability failure. This is not a statement about algorithm strength. It is a statement about what information exists in the image in the first place. Now let's look at the first failure mode in detail. Occlusion is not noise. This distinction is critical. When a measurement is noisy, it still exists. It is a corrupted version of the true value, and with enough data or a good enough estimator, you can recover from it. When a pixel is occluded, the measurement does not exist at all. There's nothing to recover from because the signal was never recorded. Consider stereo matching. The standard formulation assumes that every pixel in the left image has a corresponding pixel in the right image. For a half-occluded pixel, a pixel visible in one camera but physically hidden from the other by a foreground surface, this assumption is false. No valid disparity exists. But the algorithm does not know that. It searches for the best match it can find, and it fabricates one. The result is not random error. It is systematic error at every occlusion boundary, concentrated at exactly the locations where depth changes matter most. Sherstein and Zelinsky identified this in their 2002 taxonomy as one of three canonical stereo error sources, alongside textureless regions and depth discontinuities. And those same three categories describe where modern systems fail today. Classical methods developed three main structural responses to this. The first is explicit labeling. Kolmogorov and Zappé formulated stereo as an energy minimization where a pixel is either matched with a specific disparity or labeled as occluded, with both options competing in the same optimization. This makes occlusion a first-class citizen in the estimation problem, rather than afterthought. The second response is layered representations. Wang and Allison decompose scenes into depth order layers, where each layer has its own appearance in motion. Occlusion then becomes a geometric consequence of depth ordering rather than something that needs to be detected separately. The front layer simply covers what is behind it. The third response is forward-backward consistency. If a pixel in frame T maps a location in frame T plus 1 and that location maps back to a different point, then the cycle is broken and occlusion is likely explanation. All three of these categories share the same underlying insight. Acknowledge the absence explicitly rather than pretend it is not there. Now there is the key observation about modern systems. This failure does not go away when you switch from classical methods to deep learning. Consider self-supervised molecular depth estimation. The training signal is a photometric reprojection loss. You wrap one frame into another using the predicted depth and camera motion, and you penalize the appearance difference. But this loss assumes that every pixel in the source frame is visible in the target frame. At an occlusion boundary, that assumption is violated. The pixel that just went behind a foreground object has no valid reprojection target. The loss at that location is wrong, not because the network made a mistake, but because the supervision signal itself is structurally invalid. Goddard and other people addressed this in 2019 with minimum reprojection, which takes the best reprojection from multiple source frames, and auto-masking, which ignores pixels whose appearance does not change across frames. These are elegant engineering solutions, but they are responses to the same classical problem that Sherstein and Zalesky described in 2002. The architecture has changed, but the structural limit has not. The second failure mode is specularity. Let me be precise about what goes wrong here. Classical methods assume Lambertian reflectance. Under this model, the appearance of a surface depends only on the angle between the surface normal and the incoming light direction. The camera position does not matter. This is a convenient assumption because it means a surface always looks the same regardless of viewpoint, which is exactly what you need for stable feature matching, stereo correspondence, and photometric stereo. A specular surface breaks this completely. The highlight you see on the glossy table moves as you move around it. It is not a feature of the surface. It is a feature of the geometry of the scene as seen from your current position. If you run a stereo matcher on two images of a shiny object taken from slightly different viewpoints, the highlights will have shifted, and the matcher will try to find correspondences for features that have moved independently of the surface itself. The resulting disparity is run in a systematic way, not because the matcher is bad, but because the input violates the assumptions the matcher was built on. Aldrin and colleagues proved the worst case of this in 2007 in uncalibrated photometric stereo, where you have multiple images under unenlightening, a three-parameter family of scene transformations called the generalized bas relief transform produces images that are literally identical. You can replace the true shape with an infinitely thin version, scaled and sheared, adjust the albedo and light directions to compensate, and the images are indistinguishable. This is not a limitation of any particular algorithm. It is a property of the problem itself. The Fisher information matrix is singular along these three directions. The parameters are non-recoverable. Now here's something interesting. The same property that makes specularity a failure mode can also make it an additional source of information. If you model it correctly, when a specular highlight moves across a surface as the viewpoint changes, that motion encodes information about the surface curvature. This is called specular flow. Shandraker and the colleagues showed that specular flow carries geometric information that is algebraically independent of the diffuse shading signal. It can resolve exactly the base relief ambiguity that defeats purely diffuse methods because it adds constraints in the three directions where the Fisher matrix was singular. Cui and other people showed that polarization provides a complementary signal, constraining surface normals on specular surfaces where texture-based correspondence fails entirely. The lesson here is that what looks like pure noise under one model becomes a signal under a richer model. But exploiting it requires either additional sensing or strong priors. The third failure mode is repeated texture, and it actually comes in two flavors that look like opposites but produce the same fundamental problem. The first flavor is texturelessness. A blank wall or a uniformly painted ceiling has no distinctive logo appearance. Every patch looks like every other patch. There's nothing to match because there's no discriminative signal. The second flavor is repetition. A brick wall or a tiled floor has plenty of signal, but that signal repeats everywhere. Every patch that looks like one brick looks like every other brick. There's too much signal and none of it is distinctive. Shi and Tomasi made this precise in 1994 using the structured tensor, which captures the distribution of gradient orientations within a local window. If both eigenvalues of this tensor are large, the patch has texture in two directions. It looks like a corner and correspondence is well determined. If one eigenvalue is large and one is small, the patch lies on an edge and only the normal flow can be determined, which is the aperture problem. If both eigenvalues are small, the patch is flat and correspondence is entirely undermined. This Shi-Tomasi criterion is essentially a per-pixel certificate of whether correspondence is well posed at that location. And here's the key insight. This is a property of the image, not the algorithm. A better matcher cannot make a flat wall more distinctive. The information simply is not there. Classical methods developed several strategies to handle this. Sieff's ratio tests measurements distinctiveness by comparing the distance to the best match against the distance to the second best match. When this ratio approaches 1, the match is ambiguous. On a repeating pattern, many scene points produce nearly identical descriptors, so the ratio test correctly flags those matches as unreliable. Geometric verification using RANSAC then filters out matches that are inconsistent with epipolar geometry. And semi-global matching propagates matching costs from well-textured regions to poorly textured neighbors, using spatial context to fill in where local signal fails. But notice what all of this do. They either detect the ambiguity and give up, or they borrow information from somewhere else. None of them create information that was not in the image to begin with. So the fundamental limitation remains. The aperture problem is where texture and occlusion meet directly. The optical flow equation says that the image gradient times the flow velocity must equal minus the temporal derivative. Written out, that is ix times u plus iy times v plus it equals 0. That is one equation with two unknowns. Only the normal flow, the flow component in the gradient direction, is constrained. The tangential component, the one along the edge, is invisible. This is the motion estimation version of the edge case in the structured tensor analysis. One large eigenvalue, one small, one free degree of freedom. The classical fix is global smoothness regularization, which couples under constrained edge pixels to nearby well-constrained corner pixels. But Horn and Shunk's smoothness prior fails and motion boundaries, which are exactly the locations where adjacent regions move differently because one surface is occluding another. The smoothness prior averages the velocities around the boundary, producing a wrong answer for both sides. And this is the compound nature of the aperture problem. It sits at the intersection of texture failure because it only rises on edges rather than corners, and occlusion failure because smoothness breaks down at boundaries where visibility changes. The best belief ambiguity is the clearest example of what I would call a compound failure, where photometric and geometric uncertainty interact and reinforce together. The setup is shade from shading. You have one image of a surface and you want to recover the surface shade from how bright or dark each point is. Horn first formulated this in 1975. The problem has been known to be ill-posed in general, but Bell-Hummer, Kriegman, and Yulee made the structure of ambiguity explicit in 1999. Their result is that an affine transformation of depth replacing z with lambda z plus mu x plus nu y combined with a compensating adjustment of albedo and light direction produces a pixel-wise identical image. You can flatten the shape into something like a bas-relief sculpture or stretch it into something dramatically more three-dimensional, and photographs are distinguishable. This is a three-parameter family of the solutions, a three-dimensional subspace of parameter space where the feature information is zero. Resolving it requires breaking the degeneracy by adding ramp. Multiple light sources add more equations. Specular cues add constraints orthogonal to the diffuse shading. Strong shading priors, like the ones Sengupta and other people used for faces in 2018, restrict the solution space to a manifold where the remaining measurements are sufficient. Now let us look at how these failures play out in modern neural rendering systems. The standard neural radiance field formulation from Mayo Den Ho and other people in 2020 represents a scene as a continuous volumetric function and synthesizes nova views by integrating along camera rays. This bypasses explicit correspondence entirely, and yet the classical failure modes immediately reappear. Transient occluders, like tourists in a photo of a landmark, appear in some views but not others. Standard nerve has no mechanism for this and interprets them as part of the static scene, producing floaters and artifacts. Martin Brula and other people address this in Nerve in the Wild by decomposing the scene into a static field and a transient field. This is the layered representation of Wong and Allison from 1994, now implemented in a neurovolumetric framework. For specularity, standard nerve's view-dependent radiance is parameterized as an unstructured function of viewing direction. The optimizer will find the easiest way to explain view-dependent appearance, which is often to place geometry incorrectly so that the surface normal happens to produce the right highlight for each view. Refner from Verbing and other people fixed this by reparameterizing radiance in terms of the reflection direction about the estimated normal rather than raw viewing direction. This structural choice prevents the network from explaining highlights through geometric distortion. The same pattern holds in transformer-based stereo and optical flow. Look at the table on the slide. IG stereo from 2023 constructs a geometry encoding volume and iteratively refines disparity using a learned cost volume regularization. Raft from 2020 builds an all pairs correlation volume and uses a recurrent update operator. Flowformer from 2022 tokenizes the entire four-dimensional cost volume and processes it with a transformer. Each of these architectures encodes a specific classical disambiguation strategy. IG replaces local window search with global context. Raft replaces handcrafted smoothness regularization with learned propagation. Handcrafted smoothness Flowformer replaces multi-scale wrapping with global attention. These are real advances, But when you look at the error distributions on the Spring benchmark and on Kitty, the largest errors still concentrate at occlusion boundaries and textureless regions. The architectures have internalized classical priors in a more powerful way. The information theoretic limits have not moved. Now let me put all of this together into the unified synthesis. We have looked at 3 failure modes, each with a different physical mechanism, and occlusion, data absence, specularity, model mismatch, repeated texture, observational equivalence, but all 3 have the same formal consequence. And in each case, the facial information metric becomes singular. For occlusion, it becomes singular because the measurements that would constrain certain parameters simply do not exist. For specularity, it becomes singular because there's a family of parameter configurations, the GBR family, for example, that all map to identical images. The data distinguishes between them with 0 probability. For repeated texture, it becomes singular because distinct scene points produce identical local observations. There is no way to tell them apart from the available image data. When the facial matrix is singular, the Kramer route bound is infinite in the corresponding directions. No estimator of any form can achieve finite variance for those parameters. This is not a statement about algorithm quality. It is a statement about what information exists in the image. And from this perspective, every resolution strategy in the literature is doing the same thing, providing additional information that compensates for what the failure mode removed. Priors restrict the solution space. Alternative sensing modalities add orthogonal constraints, multiple exposures, and more equations. The right question to ask about any failing vision system is therefore not, is this ill-posed? Because almost everything is, but rather which specific parameter is non-recoverable and what specific additional assumption or measurement would restore it. This slide organizes the answer to the question. On the left column, priors and constraints, and there is priors and constraints. Smoothness priors couple well-constrained regions to ambiguous ones. Rigidity constraints resolve the aperture problem by imposing global structure. Learned manifolds, like surface-shaped priors, restrict the solution space to where the remaining data is sufficient. In the middle column, extra measurements, polarization constraints normals on specular surfaces. Specular flow provides curvature cues independent of diffuse shading. Multiple lighting conditions add rank to the photometric system. On the right, representations layer models make occlusion explicit. Transient decomposition separates the scene from occluders. Reflectance separation isolates shapes from illumination. And every entry in this table is a specific answer to the specific question: what additional information makes this specific parameter recoverable? Now let me close with the main takeaways. The 3 failure modes we studied, occlusion, specularity, and repeated texture, are not artifacts of old algorithms. They persist as the dominant error sources in modern neural systems including NERF, transformer-based stereo, and foundation models for depth. The reason they persist is that they reflect information theoretic limits, not the engineering limits. Learning internalizes the same regularization strategies that classical methods apply explicitly. It does not eliminate the underlying data limitations. And looking around, the open problems follow directly from this analysis. Multi-body dynamic occlusion in autonomous driving, Material diversity beyond the Lambertian or specular dichotomy, urban scale repetitive structures that defeat both classical and learned correspondence, and at the cross-cutting level, the need for identifiability, diagnosis for neural representations. Uncertainty estimates that distinguish between the three failure sources and benchmarks that isolate failure modes rather than reporting aggregate error. All of these questions have the same shape. Which parameter is non-recoverable, under what conditions, and what constraint would restore it? Recovery always requires assumptions because identifiability is never guaranteed from image data alone. Thank you for your listening. My speech is over. These are my references.